Welcome to this presentation in the series on step paper, specifically the 2001 paper 1, and this presentation is on question 3. So let's start off. It says sketch, without calculating the stationary points, the graph of the function f of x given by f of x equals x minus p, x minus q, x minus r, where p is less than q is less than r. So let's do the first part first, let's sketch. So we've got P, we've got Q, and we've got R on the x-axis here. And function x equals that. So those are roots, and f of x is a cubic, so it must start down here somewhere, and it must end up over here somewhere. The only way this can happen is if it comes up and turns a corner, it goes down a bit further, and goes up like this. So that's the first part done. Second part, by considering the quadratic equation f dash x equals 0, or otherwise show this inequality here. I think in these questions they try to intimidate you by a rather nasty looking algebra. Nevertheless, let's have a go. Let me change color, and let's write what f of x equals x minus p or x minus q or x minus r. Now when they say by considering f prime of x equals 0 or otherwise, I don't know about the otherwise, but you're always going to start off by trying what they're suggesting, which is find out what f prime of x is. And I can find that out first. I've got to multiply this out to be x cubed. Can we do this in one step? It's going to be minus x squared upon p plus q plus r. That's because every x squared term, x times minus r, x times x times minus p. So you can work that out there. And then there is a plus x term. And plus x term, it's pq plus qr plus pr, and then it's minus pqr. That's what function's equal to. Check that. And then if we want f primed of x, simple differentiation here, that's going to be 3x squared minus 2x upon p plus q plus r plus this rather nasty expression here, pq plus qr plus pr. Now, by considering that equal to 0, now why are they asking us to consider that equal to 0 after we've sketched this graph? Well, for this reason, because there must be two stationary points. There's a stationary point somewhere here, a stationary point somewhere here. You can't have a curve like this, cubic curve like this that has 3 roots unless there's two stationary points. There's going to be two stationary points if and only if this quadratic equation has 2 roots, and it has 2 roots if its discriminant delta, which if you remember is b squared minus 4ac, using the usual notation for a, b and c in the quadratic equation, that has to be greater than 0. So let's try what b squared minus 8 4ac is. b is minus 2 upon p plus q plus r. That's what b is. So let's take all of that squared. Minus 4 times ac. A is 3. A is the coefficient of the x squared term, times c, which is this whole expression here, pq plus qr plus pr. That all has to be greater than 0. And I'll be disappointed if that doesn't turn out on simplification to be what we want. Let's change colour a little bit because I want to do some cancelling. Well, I'll not cancel just yet. That's equal to 4p plus q plus r squared. And let's take this negative thing over to the other side. That is greater than 4 times 3 times PQ plus QR plus PR. And now I can't cancel the 4. And that is indeed the expression we were asked to prove. So we can declare victory, and we'll declare victory by writing QED, which was to be proved. Okay, so now let's look at the last part. To do the last part, let's notice that we're given that g squared greater than 4h. It's reminiscent of another discriminant, because we've got a quadratic here, x squared plus gx plus h. This quadratic is this term here, part of this overall expression. Now that is the g squared minus 4h is the discriminant of this function here. So g squared minus 4ah, if that's true, that will imply that this quadratic formula, x squared plus g of x plus h, has two roots. In other words, it's equal to x, what do we call it? I'll just call them a and b, x minus a, x minus b for some a and b. And I've got this just because that was like a discriminant. I wanted to see where this would take us. That, by the way, h is equal to ab, and g is equal to what? Minus a plus b. Right, so the condition they've given us, which is sufficient for this inequality, is that there are two roots. So let me go back, let me change colour just to make this a little bit clearer. Where will we go to? Let's go to that brighter green. And let's write down this formula that we've got, which is x squared plus g of x plus h. They are intimidating with the algebra here, x minus k. Now if the condition we're given is true, that is equal to x minus a on x minus b on x minus k. Well, this is the reason I did this was to make it similar to the thing we had to begin with. And we already have shown that if a function is equal to that, then this other nasty bit of algebra here is true. So p plus q plus r all squared is greater than 3 times this thing. So, but instead of p, q, and r, we've got a, b, and k. So now we should have, if we take the p plus q plus r and substitute it in the other algebra, we're not substituting numbers, we're substituting in other algebra, we will have a plus b plus k all squared is greater than 3 times qr plus rp plus pq. Dear oh dear, well that's going to be ab plus bk plus ak. Let's see if we can simplify this a little bit. Well, a plus b is equal to minus g. So this is minus g plus k all squared, which is the same as g minus k squared. This when you square, the minus will go away. Greater than 3 times, oops, do that one, try again, 3 and then the brackets, ab is h plus k upon a plus b, which is minus a plus b is g, a plus b is minus g, that's why I put minus g k. So what we've shown is if this is true, g squared is greater than 4ah, then this must be true. And again, that's what we have to prove. That's what we have to prove over here. So finally, we've got to show that it's not a necessary condition. Let's think about that. To show something's not a necessary condition, you just have to find some values where the inequality is true, but the condition g squared greater than 4h isn't true. And sometimes it's worth just messing around with a few numbers and see if you can stumble across something. So let's just try g equals, we'll try g equals 2k equals 1 first. So if that's so, we've got 4g squared must be greater than 4h, so we need h to be less than 1, and we've now got to show that find out g minus k squared, so g minus k squared is equal to 1 squared, which is equal to 1, and 3 upon h minus gk, don't know what h is, I'm trying to find an h here, is equal to 3h minus gk is 2, so that's minus 6. So I've got to have 1 is greater than 3h minus 6, or 3h is less than 7. So according to this, I've got to find an h which is less than 1, and where 3h is less than 7. That doesn't look too hard. Almost any h will do. So let's have h equals 0. Am I allowed 0? I think I'm allowed 0. Why am I not allowed 0? I'm not allowed 0. I'll have minus 1. H equals minus 1 I think will also do, where g equals 2, k equal to 1. And that satisfies this condition here. Oh, I'm sorry, I'm doing this the wrong way around. I've made a mistake here. I've got to show that this is not a necessary condition. So I've got to find values for which this is true, but that's not true. So I've done this the wrong way around. I've got to find 1 is bigger than h, and I've also got to find 3h is less than 7. Well, h equals 2 will do just fine here. So if h equals 2, g equals 2, k equals 1, then the inequality is true, but that condition is not true, so it's not a necessary condition for the inequality. That finishes the problem. Let me finish the presentation just by showing this set of acknowledgements, a link to the STEP page where you can find out a lot about STEP, the exam, Microrig Maths, which has a lot of resources about STEP, and the Khan Academy, which has millions, or actually thousands of tutorials, many of them on maths, which is the model for this kind of presentation. Not as good as his, but his is the inspiration. So that's the end of this presentation. Thank you very much.